Hey guys, it's Vince. Today this video is going to be an in-depth coverage of Mach 3 or UC CNC. It's really basically the same in each piece of software, Axis Calibration. Now when I say Axis Calibration, there's no way really to make a short video on this. It is a lengthy process to explain it properly. I've seen many videos. I've seen a lot of guys film their method of doing it, and now I want to discuss it because I don't like, unlike most, I don't like to just post videos to post videos. I don't like to just hear myself speak because my time is valuable just like yours is. I like to use what's already out there. If I find something that relatively explains it correctly, and then I'll give you my overview and let you guys be the deciding factor, because to me it saves me time, and if the work is already done, why do it redundantly? I think that makes sense. So, needless to say, in Mach 3, once you get your machine all built, everything is set, let's say it's taken you weeks, days, months, years, whatever it may be, to build that machine. You used a quality substrate, you're using a metal substrate so you can get professional results, you've got the rigidity where you want it to be. This process will be done regardless of if your CNC is 300 watt, if the spindle you're using is 300 watt, up to full scale Bridgeports, Tormachs, whatever you're using, whether it's a water jet, plasma cutter, lathe, router, it does not matter. I cannot emphasize that enough, guys. If it's got movement controlled by a computer and you're using Mach 3 or a motion control piece of software similar to UC CNC, you will be required to do this. And why do we do this? Well, first and foremost, we calibrate the axis to make sure that when we say in fictional time, in digital time, I should say, it's not fictional, it's more digital. When we say in digital time that we're moving an inch, we want to make sure that we're cutting an inch in real time, or we're removing enough material to give us an inch product in real time. We want to be as close to that measurement as possible. Okay, so this is where it gets hairy. And why it gets hairy is because you've just got done building your machine, you've bolted up your motors to your axis, and now you're moving and you have to calibrate that motor to that axis on your specific machine. Now guys, one thing you'll notice is I never give the actual settings on my motors other than the actual what they're actually capable of in output and what they're actually capable of in amp draw. And the reason I never put speeds up, I never put rapid movements up, is because there's no way I can tell you that accurately once you calibrate it to your table. Everybody's table is different. Hell, even if you buy the same table as your friend, odds are it's going to have some differences. These variables are manufacturing differences. This is what machining is. There is no perfect entity. There's just close and what's acceptable in tolerances. So what we're trying to do is take these tolerances for motion and make them as accurate as possible. So think of it in this perspective. When you get everything bolted up, and just because you have movement on your table, you are not ready to machine yet. Okay? I cannot emphasize that enough. You are not ready to machine when all the motors and everything is hooked up, the spindle's working, everything is looking good, axes are set, everything is moving the correct way. You are still not ready to machine. The next step is calibration. And here is the big thing. The guys that do this correctly are the ones that have a machine that produces professional results. And I cannot emphasize that enough. Okay, if you give a chef an onion and you give another chef an onion, he's going to cut it two different ways most likely, and if they both yield the same results, so be it. Typically with CNCs, it's not the case. Typically what you'll get is one guy will do things one way, one guy will do things another way, and they may or may not get the same results. So what I'm talking about here, I cannot emphasize enough. You're going to take your time. You always want to take your time with this because, again, the pickier you are, the more accurate the machine is going to be. The good thing is that using Mach 3 or UC CNC, I'm going to cover the Mach 3 version because it's basically the same in UC CNC. The good thing is that the software will take care of a lot of the math and make this process more lengthy in explaining than actually physically doing it. So what I'm going to do now is this video I found on YouTube, and I'm going to walk you through it. It has no audio, so I like that, so I can actually narrate it myself. But it does have a very good explanation, even though it has those little pop-up windows to explain things of what's actually going on and what you should be doing. So right now you can see he's going into Mach 3 mill. Okay, he's going to go into that. So I'm going to hit play, and you can see Mach 3 is opening up. Then his reset's flashing, so he's going to naturally reset the e-stop. And then he's going over there to config and then motor tuning. Okay, now he's in motor tuning. I'm going to just pause it right here. Okay, where it says steps per. This is where you calculate your steps per inch of your motors. Now guys, I never give steps per inch, even though we know the Gecko is typically 2,000 steps per inch. I never start there. And the reason I don't is because if you read this right here, steps per inch are calculated by motor steps per revolution times lead screw TPI times micro steps equals steps per inch. Well guys, this is rocket science. And why I say it's rocket science is it's theory. Okay? And we all know about theory, or at least the guys that are making money already know about theory. Theory is only acceptable if it produces valuable information in real world. This really does not. And I'll tell you why. If you set your machine up using this, 9 out of 10 times you're going to be off. And why you're going to be off is the same reason that race car drivers, when they buy a race car or buy a high-performance car, they look at rear wheel horsepower. Let's think about that for a second. I'm a car buff, so please excuse me. I'm just kind of dictating this in with it. If you think about it and you relate to it in the same way, it's the exact same thing on anything mechanical. With a car, if you buy a car with a high-performance engine, let's say it has 350 horsepower, and that 350 horsepower, of course, is hooked to a transmission. Now, what it's generating at its crank is 350 horsepower. By the time that power translates through the transmissions, the gearing, all of everything that's spinning and rotating in that transmission, it then leaves the transmission producing maybe 290 to 300 horse. You've lost power, and you didn't lose it at the crank. How is it going away? Well, let me tell you, you have mechanical loss. You're translating motion. You're doing a lot of things. You have friction, mechanical friction. All of these variables dictate to mechanical loss. So saying your car has this amount of horsepower is one thing. Saying it has this amount of rear wheel horsepower, which is the actual power you feel in your seat of your pants, that's another thing. Okay? So once again, think of your CNC in that same perspective, excuse me. It's the exact same principle. Okay, once you bolt that motor to your chassis, you essentially are going to have a mechanical disadvantage because now that motor is connected, it has a coupler, it's now connected, now it's trying to translate its motion through the chassis and all the variables that lie within that chassis, bearing movement, friction in bearings, everything. You're never getting the exact amount. Therefore, your theory may be close. This theory may produce a close response. However, it will not produce a workable real-world response 9 out of 10 of the times. So I want you to really think about what I'm saying here. The easiest way to do this calibration is the way Mach 3 is. It's the correct way. Now, why do we know it's the correct way? Well, I'm going to explain that to you too. If you think about it, okay, you would never test, you can test an engine, whether it be a motor for a CNC or a car engine, out of the vehicle or off the table. Okay? That's what that engine produces. When you actually set it up, though, you would set it up and tune that engine inside the car where everything is connected to it. No different than you would tune the motor on your table when everything is connected to it. All the transmissional parts have to be connected to it to give you an accurate result. So, if you think about it in that perspective, now it's all starting to jive. There's no point in me actually measuring a motor when it's off the table other than knowing how strong the motor is and, again, how many amps it draws so that I can set my controller up properly. Once I know that information, then I'm going to go over, attach it to my table, connect it with the coupler, and now I actually have an axis that moves, which means that motor is no longer a single entity, and this is the best and most proper way to set my machine up because I've seen motion and I can adjust for any variables. This is where the software comes in. Mach 3 is smart enough, and I'm going to click on start here. Now his explanation here, once again, we've just gone through this, and you do not need to worry about this. You do not need to worry about this crap with figuring out calculations. It's inaccurate. It's inaccurate to the point you'll get an accurate number when you do the math. It's inaccurate 9 out of 10 times once you input that number inside Mach 3. The truest, most correct way to do it, we're going to go right from here, and I'm going to hit play, and I'm going to show you. Okay. He's putting in just an average number. Now you know he didn't do the math to come up with 4,000 or 40,000, excuse me. Velocity is measured in inches per minute. The Mach 3 demo copy will max out at 37 IPM. The licensed version goes to 100 plus IPM. Again, inches per minute, guys, that's a very big variable. Okay, inches per minute basically is signifying how fast that machine is moving. I do not, and I cannot emphasize this enough, a lot of these videos get hung up on speed of machining. If you're into machining for accuracy, speed is the last thing on the list. Okay? If you're doing accurate machining, that should be the last thing you're focused on, is the speed of which the machine moves. Okay? Other than a rapid movement based upon how big your table is. Now, a guy that has a 30 by 30 inch table, let me say that again, a 30 by 30 inch table is not concerned about how fast his rapid is, because his motors will clear that table in mere seconds. Half a second probably. I mean, it just depends on what speed his motors are running based on the voltage of the power supply he's using to control his driver. A 48 volt power supply is going to fly across a table that size. Now, a table that's 6 foot by 6 foot, he starts caring about rapid movements because he has to clear that large gap quickly so that he can get to a different spot to machine if he's doing bulk projects where he's cutting out multiple parts. This is the basic explanation of that. Do not get hung up on speed of the table. Speed of the table, once again, should be your last concern, well below accuracy. Everything is based on accuracy. Otherwise, you don't need a CNC. Do not buy one. I cannot emphasize that enough. There's a lot of misinformation online where all they seem to focus on is table movement. CNCs are not designed to just be fast. Speed means nothing. It's all about accuracy. Then we develop speed after we've acquired accuracy. Okay? So take that into consideration and really think about what I'm telling you, because it makes sense. And let me tell you something else. Anybody who sold parts that they've machined, they will soon tell you that their customers aren't asking them, well, how fast did you make this? They could care less. They care about accuracy. When you develop a piece and you say, here, this is, if you're making a bracket for someone and it's supposed to be within tolerance, then you're trying to produce that bracket over and over again in tolerance. So keep that in mind. Always stay focused on the big prize, and the big prize is accuracy and the fact that the robot's doing the work for you. That's, again, huge goal. So after that, you got now your velocity. This is explained. Again, depending upon which way you went, you've got inches or millimeters per minute. So the question here is whichever, if you went imperial or if you went metric, that would just decide. That's the deciding factor of what this number correlates to. So now that we understand that, I'm going to hit play again. He's just inputting an arbitrary number. Acceleration, inches a minute. You're really not concerned with that. That's how fast everything is going to move to that speed. What you're looking at is generating a certain speed and how fast it moves to that. These settings right here, this steps per will be set later. Velocity, once again, will be set by your machine, as well as acceleration. And why I say velocity and acceleration are actually set by your machine, it's because each table is different in what it can withstand with the steppers. Steppers inherently will generate some vibration, they always will. And again, we have mechanical loss and power, which is what I explained to you about that car description, how I went into the example with that. The other thing you have to realize is with your table, there's limitations on different points you'll find on the table. You're going to find that, certain times, especially guys that are using wood and plastic. This is why I cannot emphasize you do not want to deal with wood and plastic, because the expansion and contraction is ridiculous. More so on wood than plastic, but still it's there. And that's why we look for rigidity, so that these numbers remain more consistent, the acceleration and velocity, on top of the fact that you're looking at a repeatability factor that doesn't have as much swing. Okay, so what we're looking at here with the velocity and acceleration is these settings will be fine-tuned by your specific machine. Once you dial in your accuracy, and once you dial in, and accuracy will be dialed in once we get this steps per number put in here. Once you dial in accuracy, then you can go back into velocity and acceleration and start tweaking these numbers. Now, my suggestion to you is to keep those variances small. Instead of going up, some guys will say, oh, I can machine at, 100 inches a minute or 100 millimeters a minute, and then they start, going off the chart. I'll go 50 more until see it. I recommend a small number. Do a small number, because the smaller the resolution, the easier it is to find the sweet spot without you going over. And remember, I always go back, if I find the maximum extreme, the tolerance that I can handle with a substrate and my table, I'll back off by typically 5 to 10%. That's me. That's what I do. That does not mean that's the right answer for everyone. That's just what I do. Now, will it work for you? Well, I believe it will. And the main reason I believe it will is once you find that sweet spot, and again, remember, there's variables here to take into consideration. There's what substrates are you machining? You're going to have a lot more give with wood, a softer substrate, than you would with aluminum, which is a metal substrate. So those type of machining principles need to be taken into consideration for feed rates and speeds. Once again, velocity and acceleration will be tweaked virtually until you find your sweet spot. Honestly, I have some clients of mine, that will tweak these almost daily. I have other clients of mine who leave them basically set. I have two guys that build cabinets that I can tell you right now, they don't mess with these settings. I myself, I don't like messing with those settings. I like to leave them pretty much set. I'm not a guy who likes to tinker. Once I get my machine dialed in, I like to keep it dialed in across the board for virtually all substrates. But that's me. It depends on who you are. It depends on what you're going for. You can play with these numbers until you're happy, and until your machine, you find that sweet spot, or you're just content with where you are with that machining capability. Again, is it producing the accuracy you're looking for? Is it doing it? Again, then it'll come into more of a point as you get orders. If you have standing orders or you don't, you'll know the speed of the machine dictated by what numbers you can run here. Okay, that's going to tell you mostly everything as far as how fast you'll be able to produce the parts with accuracy. And then once you get to that level, then again, you'll come in and say, okay, well, where can I, it's okay right here. What if I jump up another, I'm going to go up 0.25 to, I'm going to go up 10 inches a second on the acceleration and see what happens. I'm going from 5, I'm going to go to 10, see if everything is okay. Do I have any excess vibration? Do I have anything that, I notice that, I'm generating some type of vibration that I'm not able to do, or the table vibrates? Typically what you'll get is stuttering of the steppers. If the stepper is moving faster than the table can accept, you'll get a stuttering in the stepper. This is very common. So again, any of those type of ailments means these numbers you've gone over on. It's time to back off and find that sweet spot. Now, I will assure you, the only time typically that happens, most definitely, is when you're dealing with rapid movement. Now, when you're machining, your machine is only going to be able to cut at a certain depth, at a certain speed, unless you're a fool. And when I say a fool, if you're cutting very, very deep and very, very fast, you're definitely going to have problems. Not so much with machine movement, but you'll break bits, you'll have a lot of excess stress on a lot of different areas, and then you get a lot of strange results. So overall, most guys typically don't do that. They're usually, if they're testing a material for the first time, they usually will machine at a much slower rate, and even a slower rate of cut, because they realize that, I'm new to this, so I'm going to just do a little bit at a time, see what happens, And that's the best way to do it, guys. Always use common sense. A lot of machining is common sense. You know, if you think you can cut a 1/2 mil at a time, I would cut 2/1000 just to see what happens. If you've never used a mill, cut slower, cut smaller and slower, and see what happens. See what the results are. Okay? And then tweak up from there. It's very easy to troubleshoot machining issues if you test a raw material, you know, for the first time, or an end mill, or a combination of the both. That's the easiest way to do it. This way you can go back in and make adjustments from there based on that. And that's how these numbers will be adjusted to find that sweet spot. Okay? And again, we're going to just recap everything real quick because I'm covering a lot of information. Velocity and acceleration will be tweaked based on, again, your table. So once everything is hooked up, these numbers will be adjusted after you have movement and, of course, after we have calibration done. Okay? We want to get the calibration done, and then we can go back in and we'll mess with this. But right now, we're going to be focused on putting in our steps per inch, or the steps per number, because we really need to figure out where we're going with that. We need to make sure the table understands where we're at. So now I'm going to hit play. Yeah, now he's explaining velocities, how fast you want to get up to speed. Too fast and you'll stall. I like to use 5.5. He's just telling you his numbers, but what he's saying there is very true. You'll stall. Okay, stalling steppers, again, mechanical disadvantage. The table can only handle a certain amount. Your table will only handle a certain amount of acceleration. You'll dial that in once again as we get and set the steps per. You can see the bar graph on Mach 3 is actually being adjusted. And that's pretty self-explanatory too. Velocity, inches per minute. So you see the bar going up and then you see it going down. Again, it's pretty self-explanatory. Then as he moves the acceleration, you can see it expanding on these endpoints here. See it? Acceleration and velocity can be changed by the sliders. Okay, we know that. Of course, you're going to save your changes before exiting. And again, you know, you have access selection. So of course, if you're setting X, if you're setting Y or Z, you're going to click on that. I mean, a lot of this is self-explanatory. I'm not going to get too in depth with how that works. Step pulse, you can see these are all on 0. I leave this all on 0 as well. I don't mess with those settings. So just so you guys know, that's up to you if you want to play with it. Again, I like simple. I like accurate, and simple is my game. So that's me. If you want to master the software and tweak every possible setting, more power to you. Again, that's on you. Again, he had to, if you noticed his reset, he had to actually hit the reset again because Mach 3 already knew that he had made changes to his velocity and acceleration. Therefore, it could put the machine in a potential problem. So therefore, it's got the e-stop already triggered, which in turn he just reset. Okay, so now he went into settings. Okay, he went into the settings screen. If you want to calculate the exact steps per inch, you need to use the Axis Calibration wizard. Okay, now this right here under settings, if you look right here above the reset, there's set steps per unit, and it says Axis Calibration. Okay, I'm going to let him go right over to there. There it is, right there. Set steps per unit. Now it pops up Axis selection. Pick Axis to calibrate. Okay, if you ran 6 axis, of course, you'd have all 6 available. Right now, you've got your X, Y, Z, and A on a typical 4-axis system. So he's selecting whatever he wants to select arbitrarily to show you this. We're going to go into that. Let him show it to you. Okay, now he's showing you what he has, which looks like a lathe here. More or less, what you'd be doing is you're measuring. Now, here's where it can get hairy, okay? First and foremost, the accuracy of the tool you're using to measure the real-world movement and the resolution of that tool is going to provide you the most accurate information. Now, when I say that, I cannot emphasize that enough. That does not mean you cannot use a $20 to $40 measuring tool. That's not what I'm talking about. What I am talking about is that if you look at this lathe, it's actually pretty big, at least from this picture it looks pretty big. If he was to do an axis measurement, okay, and he wanted to see exactly where he was going with this, whether it be on the X or Y, or whatever axis point he wants to allocate this to, okay, if he only measured an inch, okay, and that 1 inch measurement, whether it be fore or aft, if he's looking at positive or negative variable, okay, and he's using a measuring tool of a dial indicator where it's 1/1000th of an inch in measuring ability, okay, that's the resolution of the dial, and he's out of calibration by, you know, we'll say 1/1000th of an inch, okay, and we'll say that this, for instance, this machine is 10 inches long, okay, that means over the course of 10 inches he would be virtually 1/1000th of an inch per inch out. So then it would be 10 inches times 1,000. So he'd be 10,000ths of an inch out over the course of 10 inches. Now, guys, I want you to think about that. That is how easy it is to amplify those kind of inaccuracies as you're machining. Okay? Guys that are machining right here, they're going to have much less inaccuracy than guys that are machining out here. Okay, so if you have a router, okay, the thing to take into consideration is that same rule applies. The farther from the center you go, wherever your spindle is, or again in this case his lathe chuck, wherever he goes with that, the farther out he goes, if that's off, the farther out the variable will be. That is why calibrating is so important, and that is why using the proper tool is so important. Now, when you're calibrating an axis, especially something like you see here, or for a CNC in general, you want to use a precision measuring tool with a high resolution. I like a 10,000ths of an inch resolution. Some guys use 1,000th of an inch resolution. It's up to you. Okay? For dollar, the difference in price is not much. And I'm going to tell you right now, the resolution will be there. That's why I like 10,000ths of an inch. The other thing you want to look at is the distance you want to measure from. If you want to measure from right here, let's say where I'm moving right now, you can see the cursor, it's actually moving up and down. That's a very short measurement. Let's just say that's 2 inches. Okay? So if you wanted to measure from 2-inch travel, that's fine. But in essence, if this is 10 inches, for instance, the most accurate way to be would to actually measure the movement at the longest range. This way you know what your variable would be at the longest range of the table to give you the most accuracy. Now, what does that mean? Well, let's think about it for a minute. If we're at here, the 2-inch range, and we measure and you measure off by 2/1000ths, that means 2 again, it's multiplied, and you figure, okay, I moved 2 inches, so you'd be 5 times 2, you'd be another 10,000ths off by the end of the table. So you really want to look at that and think about what I'm telling you. If you go the full 10-inch range of the table and you're out by 3/1000ths, okay, because you're measuring out all the way out here from the center point, that's going to give you the more accurate reading. Why is that? Because you've covered the whole table length, and if you can get that dialed in from 3/1000ths, let's say, down to, 1,000th to a 1/2,000th, you know that you can run your entire table virtually error-free. It'll be virtually perfect, and that's really what you're looking at. Oop, I hit start play there. Let me just rewind this a second. Okay. This is the interesting thing that you want to look at. Okay? You can either go with 1 inch. A lot of guys are using a 1-inch measurement. You can do that. If you want to do a 1 inch, if you want to do a 6-inch, if you want to do a 10-inch, whatever arbitrary number your table is, you can actually do and calibrate the table to that measurement. The thing to keep in mind, and I cannot emphasize this enough, you should always strive for the longest number that pertains to your table. So the longest number in this case would be the length and the width. If you have a 12-inch 12 by 12 router, let's say, you would shoot for the closest number to 12-inch, the longest number to 12. That's what you're looking for. Why? Because then you know anything beneath 12 inches is going to be dead balls on. So that's really what we're looking at. Again, every machinist typically has their own way of acceptable tolerances. If you're okay with being accurate at 1-inch margins and using that as your measuring point, then okay. Just keep in mind, very few machines, and I'm just letting you know, a lot of guys will dial it in at a 1-inch variable, get the unit dialed in. A lot of guys will go, well, Vin, I used the 10,000ths graduation resolution dial indicator, and I only measured an inch, and I got her dialed in at a 1-inch mark. Okay, but as soon as I ask them, well, did you go out to as far as you could on the table and comfortably measure it to see if that 1 inch carries over? A lot of guys don't do that. If you're looking for acceptable accuracy and you want to get as close to perfect as possible, think about what I'm saying. It's the right way to do it. The question is it applicable to what you're machining? And why I say that is a guy that's dealing in woodworking typically does not care about being more than a couple thousandths accuracy. Typically 5 thousandths is easily acceptable. Wood will change with temperature, humidity. It expands, it contracts. It's a very forgiving substrate, and therefore tolerances typically are not so critical. Now, that same guy, if he's milling aluminum and he wants to mill an aluminum, let's say a lower, he's working on a lower for an AR-15, he's going to want that tolerance to be dead balls on or damn close to it. Why? Because first of all, anything you deal in that kind of capacity, and again, I'm just throwing it out there, okay? Firearms, everything is super precise. You're looking for precision because you're dealing with a precision tool. That's what you have to take into consideration when you start doing Axis calibration. What am I doing this for? How accurate do I want my machine? In retrospect, I'm hoping I'm talking to the elite few that want their machine as accurate as possible, because I'm taking the time to explain to you in a way that will produce a machine, if you use these methods, that will easily rival that of most manufacturing equipment in production today. So if you think about what you're hearing here and you really, really study what I'm telling you, you may have to watch this video a couple times. I know when I was learning, I did, and again, I was lucky enough to have to work with machinist hands-on to see this process, because it's like I said, it's a lengthy process to explain. It's much more intriguing to do. It's actually a fun process to do, because once you feel that you've gotten your machine dialed in, it is an amazing feeling, especially when you start producing parts that you're proud of, where you know it's like, you know what, these are awesome. These came out great. Your customers, they love it. And then I'm on the right track. And once you get a feel for this, I promise you, you will not want to go back. You will not want to, 1,000th accuracy is not accurate anymore. That's the old machinist cliche, is that where you were yesterday, you don't want to be today. So if you think about it, we're always striving for perfection or damn close to it. In this retrospect of what I've just described, that will get you the closest mark to it. If you want to be the guy that measures out 2 inches or an inch and his machine is accurate at that 2-inch regimen and you're okay with that, then so be it. If you're looking for more accuracy and you're looking to get the most out of your machine, the farther from this center point you go out here, the more accurate the machine becomes. So just keep that in mind. It does not matter, again, that this is a lathe or a router. A router, of course, you'd have a spindle, or a plasma cutter, you again have the plasma here. It's the same principle. You're going to measure out from the spindle or the plasma, and you measure way out here, and if you're from your chuck or your spindle or your plasma, that if that run out is 5/10 thousandths, you're good. You're not really going to have any real problems. You'll be set. We're talking, guys, we're splitting hairs here. I'm really being precise, but the reason I'm doing that is because why the hell own this kind of machinery if you're not going to be? That's the whole purpose of owning this machine. If you do any type of surfacing with a machine like this, you will truly appreciate it, because the products you will make will be outstanding if you take the time and do this correctly. So right now he's being nice, and I'm just going to get back on track with this video. He's going over here and he's telling you basically where to measure. I'm going to click here and go to play. Okay, Now, he says move the axis in the plus direction only. And again, what he's talking about here is your axis, when you're calibrating, you really want to calibrate in both directions. That's actually the proper way to do it. Again, you don't have to. You can calibrate in one direction. I recommend both directions. That's who I am. Everybody's different. Typically, what you'll find, though, the software is accurate enough that if you do calibrate in a single direction, it should carry over into the opposite direction. Once again, guys, this is why Mach3, probably one of the biggest reasons Mach3 is so expensive. And CNC software, as far as expense, how they're so valuable, I guess that's the best term to use, is why they're so valuable is the math here is being done with the motors attached to the table. So what you're seeing visually is what you're getting hooked to the table and all the mechanics so that your accuracy will be dialed in the way it should. Okay, it's no different than when a guy takes his hot rod to get it dynoed and has it set in a car. That's what dyno tuning is for, is so that you can match everything and get it dialed in so you're getting the best performance with everything mounted in the car so that everything matches. That's what we're hoping to do. Best performance versus just an individual component. I'm going to hit play again. Okay. Only measures backlash in one direction, but there is a solution. Backlash I'm not going to get into. Again, that's a whole different video. But overall, right now, what it's asking you is how far did the x-axis move, measured value. Okay, so what you're basically going to do is, once again, on that, with that picture of the mill, if we put in there that we spaced we're actually measuring at a 1-inch movement, so to speak. We would put in there, we would actually space the dial indicator 1 inch from the actual tool. I'm going to go back here a second and see if I can pull it up. Let me just see. Here we go. If I put that dial indicator over here at a 1-inch level, 1-inch level with the horizontal plane right here to give me a measurement, put the plunger right here, have the dial indicator sitting right here, and be at this level, and it's 1 inch. We're going to then tell Mach3 to move 1 inch. And what she's going to do is the table is, of course, going to move 1 inch. I'm just fast forwarding through the video. Okay, let's see. Here we go. How far did the x-axis move? So after you would do that, it'll ask you, how far did the x-axis move? This is where that measuring instrument and that resolution comes into play. Did it move an inch? Did it move over an inch? Under an inch? Where did it move? The resolution of that tool then needs to be read, and then you put it in right here. Once you put in that exact measurement from that tool that you're using, Mach3 will go in and auto-calibrate. I'm just actually hitting play on the video right now. There you go. Now he put in here 0.502. That's what he's saying his axis moved. If he did that, okay, at a 1/2 inch, if he did that, and let's say he did a 1-inch measurement, now Mach3 is going to correlate and do the math for him with the motor attached again to the table so everything is accurate, and make that axis as true as possible. Now here, I want to show you how accurate we're talking, guys. Set steps per unit. X-axis will be set to 39840.637450199. Now, I'm not going to go into all this decimal crap, but we're talking literally hundreds of thousands accuracy here. The software is going in mathematically and calculating out a formula that most calculators won't even come close to. Okay? Would you like to accept it? It's asking you. And of course, you're always going to agree with the software because it's doing the math. It should be perfect, which it will be. And the big thing here is, even though this is perfect, you should still run this check again. And we're going to go through this. I'll show you what I mean. Now it says, if you look there, it was really quick. I'm just going to rewind that. X-axis has been set. So she went in, auto-calculated, came up with that figure, asked you, hey guys, are you accepting this? You say, yeah, I'm accepting it. Boom, done. That's it. No math, no BS of sitting there and with a calculator and hoping to get the figures right. This is the correct way to do this. Once again, There is no negating the fact you need the proper tool to do the proper job. The more accurate and the higher the resolution of the tool you use, and the better the procedure of the tool you use, you will end up with a tool, which is what the CNC is, that will yield you professional results. So please take that into consideration as we go through this. So once again, the x-axis has been set. I'm going to hit play again. Now he says, and this is interesting because this is one of the rare few videos that I found, he says you can reverse the axis and run the steps per inch calculation again. This is interesting so that you can measure both axes and check in both forms, positive and negative directions. Guys, that is the way to do it if you really want to know. I mean, if you just think logically, why measure one direction? You've already measured one. I'll measure both. See how close we can get it. That's the right way to do it. So again, you can reverse the axis and run the steps per inch calculation again. You do not have to. This is a step that he does explain, and again, he's going through with the little drop windows. Now I'm coming up. He's going to click on config, homing and limits, and what he's going to do, and I'll just let him show it to you. You can reverse the axis and run the steps per inch calculation again, and right now you can see where it says reversed. He's going to check those boxes. Watch. Yep, there you go. And then this way he can check that in the opposite direction if he chooses to. Okay, so once again, I choose the lathe because Mach 3 does not have axis calibration, so you must use Mach 3 axis calibration. So, Mach 3 turn does not have axis calibration, so you must use Mach 3 mill axis calibration. So basically what he's showing you is how to actually calibrate a lathe. Interesting. I don't have a CNC lathe, nor am I familiar with them. I don't use them personally. So what he's talking about here is for most guys that have a CNC lathe, this is very interesting for you because you can then use Mach 3 mill to calibrate your lathe in both directions. Very, very useful. Good to take notes on. Just hit and play again, getting through this. If you don't know the steps per unit, then start by setting the steps per unit and velocity low, then run the axis calibration again. Well, guys, you could split through 3/4 of this and just start there. A lot of guys, if you're using a G540, you can always start with 2,000 steps. The Gecko, in theory, is 2,000 steps, in theory. Now, it probably is 2,000 steps. The biggest problem you're going to find is that are you going to get that fully when it's attached to your machine, because no one is running these motors not attached to their chassis. So those numbers to me are bogus until I get everything hooked up and then I see the relative term of what's left. So you really have to take that into consideration and remember a lot of theory goes into producing a virtual result. And that's really what you're looking at is realistic results versus theory. This is where it gets hairy. You know, we all know certain things theory is applicable to. When it comes to a CNC, there's so many variables. I'm not a big fan of theory with CNC use, so I'm just telling you. So anyways, right here, if you don't know the steps per unit, then start by setting the steps per unit velocity low. Well, we know that already. I've already covered that. I would always start the velocity low anyways as you're going over things because, again, you're new, your system's new, you're learning. This is the smartest way to do it. You can always go and readjust those settings as you go. Okay, set low steps, set low velocity. He's just showing you there. End session. So this is the end of the video. However, what I want to clarify one more time, and I'm just going to come over here and really show you in depth how we do this. Okay, here we go. Actually, we're going to come a little more forward. And steps per unit, he's there. That's cool. That's cool. We're measuring. We're doing our measuring again. Okay, so let's say, because we've already done, and we already had it entered in, he did an arbitrary axis, which was the x-axis for this lathe, and he did his measurement. And he was okay with his measurement being what it was. He inputted that input after Mach 3 had asked, are you okay with that? I'm just getting to that point where it did that. Okay, it's asking again, how far did the x-axis move? After he already input the x-axis movement the first time, I would run this at least 3 times in both directions to give you a good feeling. That's my own standpoint. That's up to you. If you're happy with one, go with it. If you're happy with two, go with it. That's all arbitrary. It's totally up to the end user as far as what's acceptable. Okay? But overall, this is really up to you as far as how many times you want to run this program, and how, I would say, actually it's not really up to you, it's more up to the tool you're using and the resolution. If the tool you're using and the resolution is accurate as it should be, which I'll be honest with you, I've used everything from Chinese test indicators to Starrett to Mitoyo, you name it, I've used pretty much all of them. And for this type of work, they're all pretty close. I mean, I have to be honest, they're really not that far off. Now, granted, if a Starrett is a Starrett, you're still paying for the name and the history of the quality of the tool. There's no doubt it's there. But I will say, if you have access to a dial indicator with a high accuracy resolution somewhere in the 10,000s range, you are still going to have a tool that's producing pretty damn good results. So I would definitely go with that over nothing at all. Or I see guys using vernier calipers, and those are the digital calipers that you see them. That's just not accurate. I see guys using rulers, which is absolutely ridiculous. I mean, everybody, and I always get a kick out of that. If you ask somebody to read a ruler, they're always going to read it differently. The only people I've ever learned, I've had one guy that I've worked with in all my years that would read a ruler at a scientific level. And most people will say, if you say what's 1 inch, they're going to tell you this is an inch, and this guy's going to tell you this is an inch. I'm not real big on that. I'm real big on accuracy. And that's the big thing. If you're doing this and you're building this table, you're going through this kind of precision, use the proper tool for the job. Is it a cheap proper tool, is whether it's up to you or not. Again, Chinese, American, pro grade quality, whatever you've got to use a tool designed for the job. Okay, that's the most important part of this whole thing. And once again, after you do a measurement, then you would move on to another measurement and get that measurement down to where everything here makes sense. If you put in the first measurement, everything looks good, you're going to run this program again and double check the movement. How much far did the x-axis move? You ran it again after that first input entry. You're going to see if it's off. Is it off again? If it's not, then you're done. If it is, then you would go through and do it all over again. So you repeat this process real plain and simple until you get the accurate result you're looking for. Okay, I'm now going to, being this video is done, I'm going to take you to another individual who posted videos. His name is Hoss Machine. He is probably one of the best machinists I've seen in explanations. He's very simple. And again, he's using professional grade equipment. I like that because, again, just because he's using that kind of equipment, it directly reflects on the tolerances that he goes with and how he measures. Before I do that, though, I want to discuss mill tramming. Okay, a lot of guys do not know what tramming a mill is. Okay, so what I'm going to do, again, I'm not going to recreate the wheel because there's plenty of videos on YouTube, is I'm just going to give you an overview of what tramming a mill is and how important it is to tram a mill. Okay, now you got, of course, tens of thousands of different videos here on tramming a mill. Okay, most of my guys are using a CNC. Most of them. I would say that 80% of them are using CNCs. So I'm just going to come over here, a router, I should say, because you can do this with either a router or a mill or a CNC. It really does not matter. These principles would go the same whether it's actually computer controlled or if it's a standard mill. And when I say that, if you have hand controls, you would still want to square your spindle to your machining surface. Okay, now this video, I'm just going to bring it up. Again, you can look at these videos. You can look up here if you wanted to copy this or go over them. I'll put the links in the video so you guys can do that. Oh, I got to skip the video. We'll just skip it. 2 seconds. Okay. Doing just what you would do if you were watching.
Guys, Chris here from CNC.
Okay. He went through and is basically explaining his process. I'm just kind of fast forwarding to it. Okay. he's got this tool here that mounts in the chuck of the spindle and basically hooks up, and it's dual dial indicators. This rotates, of course, and in the video you'll see it rotate. He's using a piece of glass because, of course, it's perfectly flat, and he will cycle this back and forth on both the X and the Y, so that if he goes both actual directions, he looks for run out, and he centers his spindle by shimming it to make it parallel with the work surface. This is extremely important, and why it's extremely important is because mainly for the guys that are doing any type of facing, you want your facing to be perfect. This is what's going to make that's going to separate you from the amateurs, basically. If you're doing any type of facing, I have guys doing cabinetry. They're looking at them cabinets having a beautiful face to them. This is what's going to do that. You want to center this spindle on both the X and the Y axis. So you're going to go both ways. We're going to go horizontally and we're going to go vertically. And it's really easy to do. I mean, it's really not a big process. The thing with a spindle on a router is you don't have tramming adjustment screws. So that kind of sucks. And what tramming adjustment screws are on a full-size mill, you've got an adjustment capability by using and adjusting pitch and yaw on the mill. Well, our CNCs don't have that. However, everything that's going on with the full-scale mill is still going on with your smaller mill. And the big thing we have to do here is, I get asked all the time, well, how do I do that if I don't have those screws? How do we do this accurately? Well, two things. First thing and foremost, we have to analyze it from what kind of setup you have. Most spindle mounts go right onto the actual assembly. I'm going to see if I can see a better picture of his spindle. See where I can go here. He's putting his hand in there. Let's keep going. Okay. You can see he's got a mount here. He discusses using a block and drilling screws through it and tapping them, and then that will adjust the horizontal plane, meaning this way, of the spindle. Guys, you should only be adjusting your spindle by thousandths, okay? If it's way off, you're really then looking at what you did when you machined your spindle mount or what spindle mount you're using. I have purchased many of the mechanics of chassis from China, and I will tell you, even the Chinese are pretty damn close. I mean, typically it's thousandths out. I have yet to see, maybe 15 thousandths at the most I've seen. Okay, now it depends on the quality of where you're getting stuff. We all know that. But overall, this should not be that far out. So minor adjustments are all that should ever really be necessary, unless your table is like really warped. I mean, again, that's why I recommend using solid substrate tables, aluminum or steel, because they're just a truer environment to work with. That platform is much more true. It's much more rigid. It's going to yield a lot better, more professional results, especially when you're tramming. So it's very simple. You want a flat work surface that you can actually measure. You want to make sure that it's the flattest as possible using glass. He's using cards here, and the cards is to actually level the table. He wants this in a level platform. I understand where he was going with that. Most tables will be level. If not, make sure your actual platform is level prior to taking this measurement, because again, we want the spindle to be level with the table. Okay, that's the big thing you're looking at here. You want this head of this spindle cutting at a level plane with your table. That's the whole goal. A lot of 3D printer guys, they can relate to this. They're always trying to level their build platform, and that's why, because it's the same principle. You want to build on a flat, perfectly flat surface. Well, we want to cut on a perfectly flat surface. So we know then if we're surfacing this piece, let's say this was a piece of MDF or acrylic, he wants to get this flat, or aluminum for instance. That's how you get that real beautiful finish. That's how you get that true finish. So again, taking your time with this is really the best way to go. He did purchase this dual indicator setup. Now, that being said, you do not need this setup to do this, okay? If you think about it, and you really want to go the way I go, I'm not a real big fan of the dual indicator thing. I think that's a little bit much. You can get a coaxial indicator. Coaxial indicator I'll put it this way. I use the coaxial indicator to dial in everything at the firearm shop. It's definitely the way to go as far as you actually tramming a table, for the simple fact that this unit right here is 6 inches horizontal. I believe he mentioned it in the video. If it's 6 inches horizontal, again, the farther out from this center point of this chuck we go, the farther out we come out here, we're looking to center her through the entire length of the table would be optimal. But the longer you go, the better off you are. So if you said you came out with a coaxial indicator and used the test probe at 6 inches, that means for every 6 inches you could dial that in to maybe 0.010 of an inch accuracy. You're never going to see that. That'll be dead on by the time your table reaches. The longer that goes out, the longer that feeler ball goes out, and I'll show you what a coaxial indicator looks like so you know exactly what to purchase, then you'll be there. And then the next step, after you find out how much the table is out, of course, the low side is what we're going to adjust to. So if we're low on one side, we're going to bring it, down on the other or up on the other. It all is depending on which way you're trying to correct. It's always the opposite. Just think of it that way. When you're adjusting your spindle, again, he's got this block right here, and he's got screws so he can adjust the horizontal plane of the yaw plane of the spindle. Okay, and then you've got the pitch plane, which is forward and aft. Okay, but realistically, just to give you an idea of how small a movement should be, in this video he uses aluminum foil. Now guys, once again, videos are being done that they're being done by everybody of all types of backgrounds. I recommend, and I highly recommend this, use the right tool for the right job. Okay, aluminum is a soft metal. It gives. It's not really designed for shimming. Okay, you can shim with it, of course. You could shim with paper if you wanted to. Is it going to hold as accurate as stainless? No, it's not. So let's look at it from a real base theory. I'm not even covering Rockwell hardness and all that neat stuff. I'm keeping it real basic. Let's use logic. If you cannot afford the proper tools for this job, then I suggest you hold off till you can, so you can make sure your table is done right. That's what I'm here to tell you. Okay, I'm not here to sit here and show you a way that you can get by without doing it the correct way. The correct way is to shim this spindle, whether it be on the pitch axis, which is either forward or aft, okay, or if it'll be on the yaw axis, which is the left and right axis, okay. And all you would do is add shim on either side of the spindle to correlate with, to correct the movement of where it's low. Okay, so wherever she's low, you bring her on the upswing. If she's low there, you bring her up. You're always bringing her up. Okay, that's the easiest way to figure it out. Again, unless you plan on readjusting your table now on full scale mills, they can adjust the base of their table. On CNC routers, we cannot typically do that. At least I've never seen one yet. That would be an awesome feature to have. Overall, though, this process is not difficult. I will be coming out with a CNC spindle kit, which will include the shim that I recommend. I use stainless shim, and I use 5/10,000 shim. Why I use that thin of a shim, which is basically, guys, it is so thin it's ridiculous, is so that shimming becomes very easy. If you do 1,000, you're going to get there eventually. You may be over. You bleed over usually a little bit. If you're using that small, you can usually fine-tune it much, much easier. Matter of fact, I might do 1,000th and 5/10,000 shim. I might include that in the kit because it would let you really step it up at a much faster pace. But honestly, explaining this process takes longer than actually doing it. And like I said, it's fun to do because you're getting your machine dialed in. And that should intrigue you, because when that machine is dialed in, I promise you, when you start machining with it, it's going to be a really, really nice feeling knowing you're producing the best parts you can. I mean, I can't emphasize that enough. Even if you're not selling yet but are looking to sell, this is going to play a huge role in doing that. So right now we've already covered everything. This is a tool that I don't necessarily use myself. Again, it's a tool that's designed for tramming. It does work exceptionally well. I like a coaxial indicator, and I'll show you what that looks like. But overall, we shim the spindle to make sure the spindle is level with our machining surface. Okay, and that's why, again, he's using the glass. So I've covered basically everything in detail. If you have any questions, I'm sure you'll ask. Overall, though, and the main reason, like I said, that I'm not doing a video with my machines and showing you this whole process is because they've done it already. You know, there's a lot of guys that are doing this whole process, and it's done tons of times on YouTube. I just don't want to regurgitate what's already being done, and it's already there. It just needs an explanation that I feel is more appropriate to what you're doing. Someone like this happened upon this. Again, he's using aluminum foil as shims. You can use what you'd like, of course, but again, I like using what's right. I like knowing that once I go to tighten everything down, if I use stainless, if I use a much harder based steel, I don't have to worry about that shims shifting or going off in variance. Because guys, let me tell you something, when you're dealing with thousands, you tightening a bolt will throw that off. It has the ability to easily throw off all of the work you've just done. So again, and I guess I should cover that as well, once you start using and doing tolerances like this, getting yourself a nice torque ratchet or torque screwdriver is your best friend. Actually, a torque screwdriver is probably your best friend. And the reason I say that, it's much easier then to torque these bolts that are mounting the spindle, which a lot of guys ham fist, they put it as tight as they can. Your spindle is not under that kind of pressure, and it's certainly not going to move that easy. Most of these mounts, if you have any familiarity with them, they are pretty tightly fit. I mean, the clearance is very, very minimal. So once you snug these bolts, this spindle should never be bouncing around on your table. You don't have to ham fist these down, which just means you're really tightening them too hard. A nice set of torque screwdrivers or a torque screwdriver, they sell them in two different formats. Ounce inches would work perfect right here, and you could tighten one and then slowly tighten the other to the same torque, and you know you're balanced. This way, all the power, all the torque distribution that you have on this mounting plate will be even, and that way it's pulling evenly on your spindle. Now, again, I have guys that say, I don't have that, Vin. I don't have that tool. You know, that's going to cost me money. It is going to cost you money. It's going to cost you money unless you know someone that can do it. I don't know what you want me to tell you. You can get by doing it by hand. A lot of guys do. Do I recommend it? Not in the long run, and here's why. What these guys don't tell you is, and this is the thing I think a lot of these novices that are doing this don't tell you, is the fact that if you go and you do it, you know, this way using a deck of cards and all this other crap, you're going to have to do this again, or should be calibrating your machine at least once a month. I would calibrate a machine at least once a month of solid use. If you're using this machine on an 8-hour day, I would calibrate it probably every 3 weeks. And that's my own PM to the machine. A lot of these theories where you know they're showing you this process, they don't cover with you the realm of what you're talking about when you're using a machine like this. Tolerance is only good for how often it holds. You should always double check and make sure as periods of time go by where the machine is in use that everything is good. You change your end mill when it gets dull. You would check your accuracy to make sure everything you did prior to that is set. So make yourself a log and go through that and double verify everything you're doing so that you know, hey, you know what? Last, 3 weeks ago, this machine was here. It's off by another 1,000 now. Maybe something came loose, maybe this, anything. Go back over, check everything, and do it again. It's a 3-week, doing it once every 3 weeks is not every day. It's not a hard process. As you get more familiar with it, it's very quick. And again, that carries over to Axis Calibration as well. Always set a log up. Once you build this table, I cannot emphasize it enough, guys, whether you use Excel or some other digital format to record your training process in the sense of memorizing PMs, and that's preventative maintenance for your system, you should have that all done all the time. It will help you immensely, keep you up to date, keep you relative, and just make things overall easier. I like writing things down because it gives me a little bit of memory perk. As we get older, we all forget things. We got a lot of stuff in our mind. Just take that into consideration. It really will help you. So overall, we've got this pretty much set up right now, and you see basically how this is done as far as him. I mean, again, you can watch the video. He's going to go back and forth with the machine and then back and forth here. Same process. It's all been explained. I'm going to go now to the coaxial. I'm going to just show you what a coaxial dial indicator is, if I can spell it. This way you guys are familiar with what you're looking at. Okay. Now, a coaxial indicator typically, I'm going to see if I can find somebody tramming their machine. Okay. It's an interesting video right here. He's actually using a brake drum as a flat surface. Okay. Just see if it starts. Here we go. Now I just paused it. I'm going to pause it again when I can get and show you the arm. Here we go. If it will stay still. Okay. Right here, you can see where the indicator mounts into the chuck of the mill, so it's perfectly centered. And then right here, it's got different feelers. This one's about a 6-inch feeler arm, which is absolutely perfect. The reason, of course, he's using a brake drum is because it's supposed to be perfectly flat or damn close to it, and he's checking run out. So as he spins this, and again, he's got his machine on. I don't recommend doing it that way. You can do it that way if you like. Again, I don't recommend that. You just would simply rotate the feeler all the way around, and you can see how, as the video plays, I'm just going to play it for you. You can see how the gauge is actually going up and down. It's fluctuating everywhere. That's giving you your reading. Okay? And then he says, definitely off tram. It's on the y-axis, so we'll need a shim. Very, very simple. He's going to shim his machine, and he's done. But you see basically how this all goes to play. Okay? I mean, it's really not that big of a deal. You could see how the actual end mill, I'm going to just see if I can reset that again and show you a good shot. There it is, of the actual feeler. This looks like a 6-inch feeler. It's got a little ball on the end. The ball is very true. Again, this is probably a Chinese indicator. It'll work fine for this application. And you could see by him reaching this far out and covering this amount of distance, that machine, the mill, the table on the mill is very small. So that's telling him that he'll be that accurate once this machine is trammed all the way to the excess movements of what that machine can do, which means his accuracy will be pretty much dead on. And you can see why I like this, I think, better is it's just an easier system to work, especially since this actually mounts into the chuck itself. Basically, it's what you like. They're both basically the same. I mean, whether you have a tandem unit of dial indicators, one on each side, you can do that as well. It's which one you like. This is just something that I've always used myself, and I was trained on using it. It works excellent, and it's simple. I mean, what you're seeing here with the brake drum is actually a really cool idea for giving you a base. And again, the reason he's using this is because you can see right here with the slots in the aluminum that if he was to have this feeler there, it would actually hit and go down into the crevices of all these slots. So he makes his surface flat by using this, which gives him a circular platform, and then he can go in here and go right that route, and then he's good. So it's a very interesting way of doing things. Again, you always want to use a surface that's totally flat. Most mills have slots in them, so you can mount your parts and use vices and that kind of thing. If you use an extrusion, of course, it has slots in it. So you just want to take into consideration what you're doing with that, and you can see basically the process of how it's done. Okay. The other video, and this is to finalize this video because it has been long, is Haas Machine. Let's see if we can find his video. Or actually Haas Calibration. That's what I wanted to show you. He does tramming as well. But let's see if we can find his video. And the reason I'm doing this, here we go, right up to the top. You can see his hits are pretty much off the chart. I mean, this video is really good. It's a really good video. And
all right, let's make a new
he speaks real clearly. He covers it real clearly. You can see how he has his dial indicator there and everything is set. The machine. And you know what's interesting? And I got to say this in this video. For all those guys out there who think that servos and steppers, I hear a lot of talk about servos and steppers. When you look at all these machines, all of them are using steppers. And what's really interesting is how accurate this machine is using steppers. So for those guys that think, you know, servos are this and that, I hear a lot of talk about how, you know, I would say about 90% of China, 90 to 92% of China utilizes stepper motors in manufacturing. Now, some of them use encoders, we know that. However, majority of manufacturing is done in China, we all know that. And if you really think about it, they're using steppers to do that much manufacturing. And I hate to say it, I mean, as far as when people say, you know, Chinese quality sucks, this, that, and the other thing, we deal with a lot of stuff from China, a lot of stuff. And I can honestly tell you, truthfully, that if you look at the variables here with how these machines are set when they're set correctly, the accuracy is pretty damn amazing. When you look at boxes and stuff that they make, the squarity of them, everything there is virtually dead on. So when you think about that, and I'm really bringing it up to show how steppers sometimes get a bad rap, if the machine is set correctly and it's done right with the correct process, you are going to have an amazing machine. So it's something to think about when you're going to purchase, because servo motors are quite expensive. Dealing with encoders is tedious. There's, you know, positive and negatives to both. Again, there's a lot of information online, but if you're looking overall at just producing accurate parts, doing it correctly, look more at setup and taking the time to do it right, and I guarantee you'll be happy with the end result. So once again, this video, or this actual collection of videos that I've covered with you guys, has been extensive. I hope you take the time to review some of the videos that I've covered. I will put links in this video so you can go over them, and I didn't redundantly have to film a video of me doing anything, because these guys have covered it and have done it in an accurate format and with my explanation on top of, again, Haas's, he's really good at explaining this whole process. I would go with everything he says. You should be fine. The tramming part of the mill, I've basically covered. You could see what our buddy there did, and like I said, he covered it with aluminum foil and whatnot. I would just change that up. Everything he did with the glass there, that's fine if you want to use that as your base surface. But if you have any questions, don't be afraid to shoot me a question. Overall, I think now you've got a pretty good thorough understanding of how this is done and why it's done. And again, I wish you guys the best. I hope it helps you. I hope you've learned something, and I hope you research everything I tell you, because I want to show you that I want you guys to learn the right way. I want you to learn what's fact. I know when I search on YouTube for videos or have questions, I want to get accurate information, and I can't emphasize that enough. Hell, we go to the doctor today. You got to go to 3 doctors to get an accurate assumption as far as what's going on. I want you guys to have definitive results saying, hey, you know what? I can listen to him. I can validate what he's saying, and that's what I want to go with. And I can't emphasize that enough. This is not a hobby to me. It is a passion, and it's a passion because it's my livelihood. So hopefully it helps you guys. If you do have any questions, message me. You can contact me through eDealers Direct. I do apologize again for the video being as long as it is, but it needed to be this long. So take care. God bless.